So consider first example, pure rotation of a rigid body. So let's consider that this is the disk, which is a rigid body, and it's lying in xy plane. So this plane of paper is xy, where horizontal axis is x and vertical is y. The disk rotates with respect to its center O with angular velocity of omega 3 radians per second. So first question is, what is the vector representation of omega? So for that, we need to make use of right hand rule when rigid body has rotation to find out the unit vector for that rotation. So take your right hand and you need to fold the finger of your right hand in the direction of omega. Okay, and then the thumb points in the direction of positive axis for that rotation. And in this example, this vertical axis coming perpendicular to the plane of paper is z axis. So omega has positive z direction. So omega can be written as a vector omega equal to 3k, where k is a unit vector in the direction of positive z axis. Okay, for example, if this disk is rotating counterclockwise and the xy axis stays as it is, then the value of omega will be minus 3k, because at that time when we bend our right hand fingers in the direction of rotation, then thumb will point towards the paper, going into the paper, and that's negative z axis. So once again, in this example, omega is counterclockwise, so the direction of omega is towards positive z, that is perpendicular to the plane and going up, and its magnitude is 3k. Let's consider point A on the disk. The position of this point can be defined with respect to position vector R A. Okay, we assume that our origin is centered at O. Again, even though I have drawn it here, you can imagine that this origin is actually at the center. Okay, so with respect to the origin, the position of A is defined as RA. And now this is omega. So the velocity for direction for V can be obtained using the equation. Velocity of point A is nothing but omega cross RA. Okay. So where omega is perpendicular to the plane of paper and R is here. So if you to find this direction as well, it's omega cross R. So we need to, it's very difficult to explain here, but if you take your right hand, point in the direction of positive omega, and then cross bend it towards R, and then the thumb indicates the positive direction of velocity, which is perpendicular to R and pointing in the direction of rotation. So this is the direction for velocity of A, and its magnitude can be calculated using VA is equal to omega cross RA. So remember this concept: when any link or any rigid body is under pure rotation, then for the velocity of any point on the rigid body, it can be obtained by defining a position vector. Let's say if this is point B, it can be defined using a position vector and the angular velocity using the cross product equation, which is omega cross RB, if it is for point B. Okay. You can consider any other point on the disk. Let's say consider one more point here, that is point C. Okay, and the position of C with respect to O is RC, and hence its velocity is perpendicular to this position vector and points towards the direction of rotation. So its velocity is here. This is velocity of C, and it can be written using vector equation as omega cross RC. So remember this concept: for any point, it's omega cross R if the body is in pure rotation, where omega is the angular velocity of the body and R is the position vector for the point on for which we are calculating the velocity with respect to the center of origin. So this topic is about relative motion analysis. So let's apply the relative motion analysis to first only translation motion, and then we will apply it to general plane motion. So this is a train. The train goes towards right with the speed of 60 miles per hour. We define our coordinate system at this point where x-axis is horizontal and y-axis is vertical. So the train has the only x component or ith component of velocity, and jth component of velocity is 0. In fact, this observer here is at the origin, so he is our fixed reference point. He does not move anywhere, so he is at the origin. Now consider two persons on the train. Person A is sitting on a chair in the train, so he is not moving relative to train, but he is actually moving with the same velocity as that of train. So the speed of this person is 60 miles per hour and the velocity of this person is 60 I, where I is the unit vector in the direction of x. There is So consider two persons, as I say, A and B on the train. Person A does not move, so his relative to the train, so his speed is 60 miles per hour. Person B runs inside the train, so his position can be defined relative to person A. If person A observes person B, then position of B relative to A can be defined using this position vector. And you are familiar with this notation that this is position of B with respect to A. Okay. Now, as this person runs inside the train with 5 miles per hour towards right, this position vector changes, and if we take the derivative of this position vector with respect to time, we get the velocity of B relative to A. So let's say this is that velocity VB relative to A, and it's given by phi I, where I is the unit vector in x direction because everything is going towards positive x. Okay, so that's how we write it. But now the question is, what is the absolute velocity of B relative to fixed reference point? In other words, how would this person observe the B running inside the train? So according to this person, what is the velocity and direction of B? So in order to find that, we need to find out what is the velocity of the train or person A relative to the fixed frame. So let's say this is the reference point. So this is the velocity of A. That is the entire train or the person sitting on the train, because everything is moving at the same speed, and this is 60 I, okay, because it's also going towards right. So now the absolute velocity of B relative to fixed reference point is the resultant vector which joins fixed reference point with the point B. And this is written as VB only. When anything is relative to absolute reference point, then we don't write relative to reference point, we just write that point. That means it is absolute velocity. When it is relative to something, then we write slash and that point with respect to which we are defining the velocity. So if we need to write down this as an equation, then we can say that velocity of B is nothing but velocity of A plus velocity of B relative to A. Again, this is not new. We have seen this in chapter 12. Okay, so for the relative velocity analysis question. So now the absolute velocity of B is 60I plus phi I is equal to 65I miles per hour. That means this person will observe person B running at 60 miles per hour relative to the fixed reference point. Okay, now let's consider the another hypothetical situation where this Ferris wheel rotates with respect to its center at angular velocity omega AB, where AB is nothing but this is the cabin B, and AB is a line that joins this cabin with the center line. So basically it's the angular velocity of this line or this link, but then all the links are connected to the same center point. So in fact, whatever is the angular velocity of this link will be same as the angular velocity of the entire Ferris wheel. So you can say that entire Ferris wheel rotates counterclockwise with omega AB equal to certain angular velocity. But this Ferris wheel is not fixed on the ground, but this Ferris wheel is kept on a giant truck. Okay, and the truck runs towards right with 50 miles per hour speed. And we also have our same fixed reference point and the observer sitting on the bench here. And this axis is x and this is y. So the velocity of the truck is 50i because it's along x and unit vector for x is I. So now the question is, what is the absolute velocity of a person who is in this cabin B? So now for that, we need to find out what is the relative velocity of the person in cabin B with respect to the center of the Ferris wheel. Now this is the example of pure rotation. So velocity of B relative to A, so it's called VB with respect to A, can be obtained using cross product of this link omega AB with position vector that goes from A to B. So it's RB relative to A. You have to be very careful in terms of the direction of position vector. It's position of B relative to A. So B with respect to A, that means arrow goes from A to B, where so that's how we define the position vector, relative position vector. So this velocity is the relative velocity of B with respect to A. But then our question is, what is the absolute velocity of B with respect to the fixed reference point? So for that, we also need to consider the velocity of A because A is not fixed. The A is moving towards right with the same speed as that of truck. Okay, so velocity of A is 50 miles per hour. So velocity of A is 50i. So the absolute velocity of B with respect to the fixed reference point is nothing but the velocity of A plus velocity of B with respect to A. Okay, so that equation can be written here as VB is equal to VA plus VB with respect to A. And then if I further add the expand this equation, then it is VA plus omega AB cross RB with respect to A, and that's the final answer of this equation. So if you look at the motion of the B, what do you think about the motion of the B? Because B is a rigid body, let's consider the person or the entire cabin. Does it undergo pure rotation? Does it undergo pure translation, or it is the combination of rotation and translation? That is general plane motion. You can pause the video and think about it before I give the answer. So the correct answer is B has both rotational velocity, pure rotation because it rotates with respect to A, but then A itself has translation, so B is under general plane motion. And this is the equation that we use to calculate absolute velocity or relative velocity of an object that undergoes general plane motion. Okay, if we assume that for some reason truck stops moving, so the velocity of the truck, this becomes 0, and so as A becomes 0, but then the Ferris wheel keeps on rotating, at that time this entire term we don't have to consider in the equation, and the velocity of we don't have to consider VA, then the velocity of B will become omega AB cross RB with respect to A, which is nothing but the equation for pure rotation. Okay, this is the case when the truck stops. But if that's not the case, then you need to use this equation to calculate the absolute velocity of B. So once again, if this concept is not clear, feel free to play back this video one more time and go through this concept, because all of our next few examples and in-class exercises are heavily based on this concept. So remember that when a body has both rotation and translation, then the absolute velocity is velocity of A and the velocity of B with respect to A. We will make extensive use of this equation for the next few examples. And if we apply the same equation to acceleration, then it can also be written as acceleration of B is equal to acceleration of A plus acceleration of B with respect to A.